We have researchers from 8 different departments at Aarhus University, and also affiliated outside of Aarhus University, or partners outside the university. My name is Morten Ambye-Jensen. I'm heading the center. I'm also associate professor at the Department of Biological and Chemical Engineering. And I'm working on some of the technologies that we are looking at to convert biomass into multiple products within the center. So before I set the scene, I would just like to say thank you all for joining. 52 participants have signed to the webinar. I'll hope the number of actual attendees will increase a little bit over the next few minutes. But it's a really interesting group of people looking at the participant list. So we have a lot of people from Denmark, but actually we also have colleagues or potential partners from outside of Denmark, Germany, France, Ireland, Sweden, and as far as well as Sri Lanka and Bangladesh. So a special welcome to all of you. And from Denmark, we are broadly represented in both industry and interest organizations, local authorities from municipalities, and of course also research colleagues. So welcome everyone. I will say that so we will record the session, so you know, and please mute while the presentations is going on. You're welcome to add questions in the chat, or ask questions in the short times we have between the presentations. We will also have 15 minutes in the end if there are additional questions, and everything beyond that we can take in. You are welcome to write us emails and get the contacts of the persons that you're interested to talk to. So in that way, creating and broadening the network. I will just use 1 minute on setting the scene before we go to the actual program. But I'm a process engineer, chemical engineer, and I look at production systems and how they fit into future production and consumption systems. And I think it's really important, the point about how carbon can only come from renewable resources in the future, and for that matter, biomass is a really important supply of renewable carbon until we have efficient additional technology to, for example, capture carbon from the air. But that's still in a somewhat far future. So moving from fossil to bio-based materials is essential, and this figure shows nicely how carbon can go through biomass into renewable carbon and into all the products we need, including materials. But we also need to couple that with recycling systems and also the renewable energy systems of the future. Integrating solutions like Power-to-X will be important. So that's a big system. On top of that, we need a sustainable food production at the same time, which challenges this development. We also need biomass for food, etc. And for today's topic, we will talk about these other materials in the building industry, in other areas where we need materials to substitute fossils or just make it more sustainable solutions. And the biggest challenge may be that all of these needs to happen within our planetary boundaries that are increasingly under pressure. So So we really need to develop good sustainable systems and make them circular in order to have a chance to keep the same materials in the future that we or the same services at least that we're used to, and maybe also discuss if that is needed. Okay, so that was the broad picture from my side. We'll here we have the program for today. So the first two presentations will be about the bioresources for materials in the future, especially looking into agriculture and the use of land, with special attention to Denmark, but maybe just as a case and inspiration for our international participants. And so that will be Uffe Jørgensen from Agroecology and Claudia Nielsen also from Agroecology. Then we'll go into the regulatory landscape, and we have Lau Reffensø with us today from the Advisory for Sustainable Building. I'm not sure if that's the correct translation, but more or less, I guess. So he will tell us about the regulatory schemes that are being rolled out on especially the building materials. And then we'll have two presentations in the end, one by Julian Christ from Copenhagen University, who's working with biobased boards from grasses and non-woody fiber material. And I will also present in the end the work that I'm involved in on using grass fiber through green biorefinery technologies for also producing biomaterials at the same time as we produce protein for feed and food. So that's the program, and with no further delay, Uffe, I will hand it over to you, and I will stop sharing and you can share your presentation.
Thank you, Morten. Let's see if it works. Do you see my screen?
Yes.
Great. I will dive into the bioresources that we can extract from agriculture. It's Denmark that has our focus, and we are mainly an agricultural country. We have quite small areas of forestry, but a large area of agriculture that maybe can supply a lot of biomass for the different bio-based sectors. But this is a question that is often discussed, and there's a lot of uncertainty about the available resources. So let's see what we think is realistic. But before I dive into these details, I think it's nice to have an overview of what are the expectations in general to the bioeconomy, because we are going to turn over to the bioeconomy from the fossil economy that we have been reliant on for 100 years, and it's a big task to change that reliance into using a lot of biomass. And as you can see here, there are expectations that we can do that in cooperation with the renewable energy that has to also supply a lot of input for materials and energy. But it's really difficult to have enough resources for this development. The role of agriculture is then to supply a lot of biomass in cooperation with forestry and maybe also aquaculture to supply all of these goods that you see in this picture. They are all bio-based and do it in a sustainable way. And this is the challenge that we have to look at. But how do we supply yet another sector? We have been supplying the bioenergy sector for some years, but if we are also going to supply the biomaterial sector, which at the moment uses something like 10% of the oil that is extracted, that is going to be substituted by biomass or other carbon resources. And we already know that Danish agriculture is quite contested in sustainability aspects. And this is because we have 61% of total land cover in agriculture in Denmark. And of those 61%, 80% is grown with annual crops, which are the ones that are difficult because they have a tendency to leach nitrate and also to reduce the content of carbon in the soils. And there are several problems related to the annual crops. But of course, we need some of that, but maybe not 80%. We have a long coastline with shallow fjords. We are therefore in a difficult position to fulfill the EU Water Framework Directive, which we should fulfill in 2027, but we have really difficulties in reaching that. Also, the EU and national climate policies are challenging for agriculture, and there are also wishes for groundwater protection. There's a poor biodiversity, and maybe lastly, maybe surprising because we think that it's a very efficient agriculture we have. It's actually not very resource efficient, and I'll come back to that because there's maybe a bit of hope that we can do things much better than we do today. First, a little bit of insight in the challenges, and then we can come back to the hope later. This is Denmark, and the yellow part is agriculture, and you can see this is quite a big share of it. But it's challenged. As we said, the blue areas here need to reduce nitrate leaching, and it's a very big share of the total area that is going to be changed in some way. It's a big discussion how this can be done. And then we have the wishes for nature protection, pesticide-sensitive areas that have to be protected with respect to groundwater protection. We have very carbon-poor soils. We have carbon-rich soils, which also have to be changed in management. And then taking all this into consideration, there's only a little bit of yellow land left, which is the robust agricultural land that can be produced as we used to do maybe. And we have to do new management in the red, blue, green areas. So coming back to the hope, I think photosynthesis is the hope that we have to focus on because it's photosynthesis that is going to supply the carbon that we need for the future bioeconomy. It was also photosynthesis that created the fossil resources, but we have to use the biomass more directly now. We can find species like Miscanthus on this picture that have a very efficient photosynthesis. We can also find varieties which are slightly more efficient, and that's fine. We should do that. But what I think we are forgetting in that development is that at a system level, Danish agriculture has not been very efficient on carbon capture because we have been focusing on some very specific products that agriculture could sell on the market, which is fair. It has never been the focus of Danish agriculture to optimize carbon capture, and therefore we have these yellow fields in August, September, 2 very good months for carbon capture via photosynthesis, but we are not utilizing that prospect. So therefore, we have had experiments at Aarhus University since 2012 on how we could optimize the use of agricultural land. As you can see from this picture from September, we have very different choices of having green, yellow, or brown fields that have a very big difference in carbon capture. And the results from these experiments showed that we could more or less double interception of solar radiation by using grasses that cover the soil and produce photosynthesis over the whole season, compared with the normal annual crops like wheat on the picture. And that doubling of intercepted radiation also caused a doubling in biomass productivity, so that you can see grasses produced in our experiment something like 20 tons of dry matter per hectare, which is much higher than a conventional crop rotation, which have wheat and barley and rapeseed. It's not very different from maize silage. Maize is also a very efficient crop in carbon capture, but maize is not very good at keeping a good household of nitrogen. There's a high loss of nitrate from the root zone of maize, and therefore the sustainability of that production system is not very interesting. It's not only increased carbon capture and reduced nutrient losses that can be obtained by shifting from some of the annual crops into perennial crops. It's also much lower use of pesticides. It's slightly increased at least, biodiversity. It's reduced soil erosion, and quite interestingly, I think also increased water infiltration capacity, which is something we need when we have heavy rains in the future. So now the question is how we can utilize much more grassland and maybe other perennial crops that are not fitting into the usual system of producing grains. And therefore, we have had a lot of focus on developing green biorefineries, which we think can disrupt the way we produce in the rural landscape. We can turn some of these new types of biomass into a lot of new products that, of course, take some time to develop, but I think Morten will give some comments on that. So I will go on with some analysis. We did some scenario analysis on future potentials on agricultural land for biomass production. And there's, of course, a lot of details behind that that you can read in some reports. But the short version is that we had 3 main scenarios: one business as usual, and then a biomass scenario using a lot of changes in agricultural production to optimize productivity. And then we had the extensification scenario, also optimizing productivity, but also taking a lot of considerations for environment and climate and biodiversity. And we also had some changes in animal production, which can change the way we also need to produce crops, because there's either an increase or a decrease in demand for animal feed. The short version is the that these results show the potentials of biomass in 2030 compared to the approximately 2 million tons we have been using earlier. We can triple the use just by using more of the straw and more of the manure. But if we also change the way we produce crops, and you can see there will be a much more green crops in the system, then there will be a potential for up to 7 times more biomass than we are producing today. It's still a big question whether there will be enough biomass for all sectors. You see this very complicated picture with the different sectors from transport to chemical industries, to buildings, to plastics, also to carbon storage. I think it's very interesting to have this complete picture. And when we did this analysis, we saw a demand for using direct air capture even in the most optimized biomass scenarios in 2050. But we still had some unused potentials of biomass, for example, cellulose and hemicellulose that could maybe be used in the sectors to try to avoid direct air capture. Direct air capture is very expensive and also demanding a lot of resources, so we should try to reduce that. Finally, I will just show a few slides of how we could also quantify the impacts of these scenarios on nature in this case, and especially the extensification scenarios released a lot of land to be used for nature purposes and biodiversity. And this is, of course, a political discussion, how much should be allocated for nature. But as you could see, there was still quite a nice potential for biomass in the scenarios of extensification, even though we release a lot of land for biodiversity purposes. Also, we quantified a significant impact on nitrate leaching, greenhouse gas emissions, which in some of the scenarios fully fulfilled the prospects in the agricultural the agricultural deal, which politically was agreed on in 2021, and this would be a nice way to fulfill those demands, because this will this can be implemented on the agricultural land that we have today. So to conclude, I think that it's possible to optimize Danish agriculture to deliver both carbon for new biomass products and also ecosystem services by optimizing the solar radiation capture and producing soil carbon storage, less nutrient losses, less pesticide use, and increased filtration capacity of rain, and increased biodiversity, which in turn can increase farmers' license to produce, which is quite important for the farming society. Thank you. That's all from my side.
Thank you very much, Uffe, for the nice presentation. Due to time, I would like to ask you to put questions in the chat. And Uffe, if you can, during the presentation, have a look at also that, I will also have a look. But then we'll continue directly to Claudia Nielsen, from Department of Agroecology in Aarhus University. So Claudia, you can share your screen.
I'm working on it.
Yes, we see it. We see it.
But that's
Perfect.
good. That's good because I can't see anything.
Yes.
Yeah.
You can start.
Good, cool. Yeah, hi, my name is Claudia Nielsen, also from the Department of Agroecology of Aarhus University. And I will just quickly present a bit about the different paludiculture crops for biomaterial production. I will not go into super depth, but just, to provide an overview. And the big question always, in case you don't know yet, is what is this paludiculture thing, which got popular. It's actually a fake word that was invented by Hans Joosten from the Greifswald-Meyer Center some years ago. And it's based on palus, the Latin word for swamp, and culture, to cultivate something. So meaning that we try to cultivate something on a very, very muddy area. In this case, it's peatlands. And I will come to that in the next slide. But the principle of paludiculture, there's a long definition, is basically that you try to preserve the peat body, at least. So it's not emitting any longer or subsiding or degrading in any form. Ideally, it could be renewed peat growth, but this is not always possible due to, baseline circumstances. It's nothing new for most people now that drained peat soils are an issue, environmentally wise, with regards to greenhouse gas emissions, water storage capacities, of course, nutrient release, coming back to the problem with the bodies of water. Worldwide, it's assumed that drained peat soils emit about 5% of the total greenhouse gas emissions, which is only from 3% of land area. And if you look at these maps, there's those 3% are mainly based in Siberia or Northern Hemisphere, Russia, Siberia, Canada, all those areas. But these are not the drained ones. The drained ones are those that we have in Europe, in America, in Africa, and Indonesia. So it's those 0.3% that emit so much. So paludiculture could be an option to stop these degradation processes. And it's nice to grow something on wetter peatlands, but it would be even better to utilize the biomass from it for something. And this is actually not really a new thing, because now when we start with the first example, which is reed, you all know it. You all know reed for thatching. Reed is one of the oldest biomaterials that have been used in building and construction. People from Mesopotamia have built their houses. People in Africa also built their houses of reed-like materials. In Europe, we have it, as I said, for thatching in basically all countries. So this is the closest option for biomass from paludiculture. And interesting is that nowadays, most reed comes from China. And the thatchers say it is at a poorer quality than before. There is some reed cultivation in the Baltic states, quite big. But it's not, they can't cover the demand. Also, I'm not sure if it's still actual, but in Western Jutland in Denmark, there has been or still is some smaller scale reed production for thatching. It has a nice benefit that usually you harvest a crop during winter when the water is frozen, so you can drive with special machinery on it. This is a big advantage as compared to the other crops that I will introduce in a minute. So, so when I now come to the next, which is cattail or taifa, you also have seen this everywhere. It's funny playing with it and spreading the seeds when you are a child. But the interesting thing with cattail is that it is insulated in itself. As you can see of this leaf picture, like the transect of the leaf, it is very, very porous and filled with small other things that make it ideal for capturing air. So TIFA is nowadays mainly used for insulation materials, insulation boards. You can have it like to blow into your wall. Different board types, and I know that in the Netherlands they wanted to build a factory just producing TIFA boards for insulation. Also Saint-Gobain, the very big, they make gypsum boards and all other building stuff. They were looking into TIFA already, but the challenge for them is that they can't find enough areas with TIFA cultivation because they require many hectares to get the factory running year round. So they would like to do it. They don't find the area yet. So there's a potential. Very nice plant. When we now move on to the tall sedges, you have probably also seen them, those funny bumps in watery areas where especially farmers are annoyed of, because if you want to go and mow, you automatically drive into it. But still, those sedges, which also are difficult to get rid of, if you think of biodiversity, how should your peatland look like? If it's wet, could be used for fodder. They do it. I doubt how good it is, but especially for energy and the pulp and paper industry, because it has some very nice features that make it suitable for it, and probably less well digestible for animals, but okay. If we now come to the most famous of all paludiculture crops, or also peat plants, the sphagnum. That's where we basically see the biggest potential at the moment, because peat is mainly used for horticultural purposes. You can't really think of something else yet. At least gardeners are, it's a tricky challenge for them because of the water preserving and nutrient preserving also properties. So this substrate needs to be replaced in many countries, latest by 2030. Companies are moving outside the European Union to still be able to provide some substrate to the European market as well. But the need for sustainability yields for a new solution. And there the living sphagnum moss in sphagnum paludiculture could be a nice substrate, because it basically has the same or similar, very, very similar features to dead peat as a substrate. So there are some trials in Canada and also some trials in Germany on 10 hectares, 15 hectares. It's working nicely. The yield is, I'm not presenting any yield details because they vary, but it's promising. It's very promising. And because of this sponge-like capacity it has, it also has some other potential, a bit more fancy applications actually. And this is diapers. Diapers, it's not even very new, because it has been used a lot during times of the First World War as diapers for the kids, but also as a plaster for the wounds. All the nurses went out to collect sphagnum because it had so broad application. And people are again working on making it a thing. I think it's good. I like it. Then also it's used for clothing, again for babies. This is from the First Nations of Canada. And if you have a small child and you look at what this is supposed to do with your child, you would maybe consider getting such a thing, because it can make wonders. More concentrated sleep, great. And also because of this absorbance capacity, sanitary pads. So this is also something that is coming. It's more and more developing. It's again not even a new thing because it was used in times after the First World War, disappeared and is now coming back. So sphagnum can do everything where you need high absorbance. Again, a different type of paludiculture crop, but also with an increasing demand, is sundew. Very tiny plant, very pretty, people like it. But sundew has some nice medical properties, and that's where the demand for more sundew cultivation on wet peatlands is coming from, because right now it's mainly from wild picking, but wild picking is in conflict with nature protection. So they now would like to establish more sundew fields to avoid the conflict with nature conservation, but still get more out of the plant. It's mainly for coughing medicine. Sundew is very good if you have coughing. Also because some yeasts are interesting for the enzyme chemical industry. I'm not an enzyme specialist, but this is an emerging paludiculture crop. And lastly, this is the last one, the black alder tree. If you have or had a child at a Rudolf Steiner school, you have come around this very nice furniture style. And the big advantage of black alder tree or wood is its very high value. It's not cheap, it lasts forever. It's living in inundated areas, basically. It's growing very well, and it might have an advantage for forest peatlands, for carbon credits, for all the forest certifications. So this goes into another direction, but is still a paludiculture crop. So in theory, you could build a whole house out of paludiculture crop. For the materials, the Germans have done it with the Paludi tiny house. They have a website, you can buy it. It's nice. It's to show that yes, you can utilize the biomass so well that it's useful. But still, there are many open questions, and they have started a lot of pilot projects in Germany. So all in all, there are more than 2,000 hectares of drained peatlands to be rewetted for paludiculture crops for biomass. This is just an example from Schleswig, where they focus on a project on 300 hectares, more 400 hectares, on the harvesting and transporting of the material, because that's still a problem. Yes, you can grow it, but you need to get the biomass away from it to a process facility or whatever, and harvest is tricky and transportation is expensive. So they are trying to look a bit more into this while also doing biochar or grass pellets and other interesting things. And there's this 750 hectares big project in Brandenburg, which is more a demonstration area. It will have an advice center. So people here working on municipalities or companies, this training on advice for sustainable peatland management could be interesting to visit when it's a bit more mature, because it just started 2 years ago. And they focus on the building and installation utilization of paludiculture crops. So you can see those projects, they complement each other. But also, I have just highlighted it in red, the grazing by water buffaloes, which is also a type of paludiculture crop, because you are producing meat or milk. Very nice. And the last example of some projects, again in Germany, in Mecklenburg-Vorpommern, where they have 800 hectares with a focus on insulation and packaging material. So if you need some inspiration on what to do with these areas, I think it's worth visiting those projects. However, while this sounds nice, of course, there are some challenges. You have a very nice water buffalo baby calf there. Looks a bit like Dobby from Harry Potter. But challenges are coming mainly from agriculture because of the competition for land area, in particular when area is owned by small family farms. Small family farmers are not that likely to get rid of 1, 2, 3 hectares as would be estates or so. And you also have the challenge of the competition with nature conservation, because they want to keep it for nature, for rewilding or just rewetting. So yeah, it's tricky, and it's a politician's problem, not my problem. But there are also chances. Of course, it's the government, municipalities, and the larger landowners that might potentially have those areas. It's also the chance of a market, more awareness for sustainability on the materials you choose for whatever, clothes, construction, furniture. And there might be chances, as I just mentioned, with the black alder on the carbon credits and the peat forest biomass. Yeah, so if I now just wrap it up as a type of facet, I mean, you can see there are some very, very large-scale pilot projects, not just in Germany, but they are big. They got an awful lot of money for those. The market development is in progress, and there's also the stimulation by product development because people are asking for sustainable alternatives. But ultimately, it's a political decision, and there's not much political decision made at the moment. So we need to continue discussing all this with relevant stakeholders from material side, from policy, from the nature side, and also from the agricultural area. Good. Thank you very much.
Thank you, Claudia, for the presentation. If you have questions, you are welcome to put them in the in the chat. I think we will carry on to the next presentation. So now we heard about the possibilities for biomass that could be available in the future in larger amounts for new sustainable materials. But we'll invited Lau Reffensø from Rådet for Bæredygtig Byggeri, the advisories for sustainable building. Lau is technical manager there, but if you can share your presentation, Lau.
Yes, I'll get right to it. Is it? Can you see it now?
Just a second. It will come.
So
I can see it.
Perfect.
Yes.
Perfect. I'm from what we translated into the Green Building Council Denmark, because it's the international name of our kind of associations. Green Building Council. You have green building councils in most countries these days. So I'll be talking about the building industry, and specifically about the Danish building industry. But what is going on in Denmark is a blueprint for what is going to happen in Europe, all of Europe, for the next coming couple of years. So it gives you a really good map or a roadmap for what is going to be the industry in all of the countries in Europe. So just a little bit about us. We are a non-profit membership organization. We were founded back in 2010-11. Today we have about 800 members in all of the building industry in Denmark. So that's for building component producers, contractors, architects, engineers, and building owners all over the value chain in the building industry. We do a lot of stuff, but I have been working primarily with DGNB certification. This is a certification scheme for sustainable buildings, actually based in Germany, and we have a national adaptation of it. It is an international global certification scheme, while it's not as famous or known as the American counterpart LEED or the British BREEAM, but it is very, very large here in Denmark and also in EU actually. So to get into the meat of it, so I have been working. I'm an engineer by trade, and I worked as a consulting engineer for years, and then about 10 years ago, I was hired by the Green Building Council Denmark, and to work with DGNB certification, because it was very, very new at the time, and it was based on trying to change the definition of sustainability from a focus on energy efficiency to focus on CO2 emissions and life cycle perspective. And it was brand new at the time. There was an European standard for how to assess the environmental quality of buildings based on an LCA perspective, and also an environmental standard for how to make environmental product declarations for building components, building materials. And we started back in 2011, 12. Very basically, now it's a part of the building regulations in Denmark since 2023. It's going to be even renewed here in 25. I'm going to get back to that. But also on the EU, it's a part of the new EU building directive that all countries in Europe must set a similar roadmap as we have in Denmark and implement limit values for the CO2 emissions from buildings based on a life cycle perspective. And they have to do it at before 2030, fully implemented. So what we have achieved here in Denmark is like, we have been at the very forefront. The Nordic countries, France, Belgium, have also implemented similar or parts of the similar structures, but or are planning to do it. But we are like very early on the change curve here in Denmark. So what is it specifically? In 2023, there was a new addendum to the building regulation that all large building, more than 1,000 square meters, must comply with a limit value of 12 kilograms of CO2 per square meter per year. So now we have a specific way to calculate CO2 emissions from buildings, and we also have a specific reference you have to meet. So this is like a minimum performance regulation. And what is included is trying to have all of the different life cycle stages in a building's life cycle. So we have the production of building materials or components. We have the use phase of the buildings, the operational energy, and if you have to renew specific components. And we also have the end of life, the waste handling of the building materials. We are in Denmark, we use a 50-year reference period. So we calculate for the first 50 years, and that is more or less the standard in all of the world. But it could have been 60 years or 100 years. There's no specific reason to have 50 years, except that it is long enough to take in the operational phase of the building, but not so long so you get lost in how to project the energy system 100 years out in the future. We don't know how it's going to look in 100 years. biogenic carbon in this system is following what we normally would call the -1 + 1 rule. So the biogenic carbon embedded in a building material calculated as negative in the production phase. So if you have wood or some kind of insulation materials or whatever, you of course calculate the direct emissions, but the carbon captured in the material is calculated as negative. And then at the end of life, we assume that this is going to be burned or decomposed in some way, so the CO2 is going to be emitted again sometime in the future. And in an overall perspective, we calculate the biogenic carbon as neutral in the life cycle, which is quite strange, because when we do it in the national what do you call it? The national CO2 calculations, the ICCP calculation rules, you can take into account if you store the carbon for more than 30 years. But in the building industry, we calculate it as neutral, even though we might store it for 100 years or 200 years. There's at least a possibility for that. In Denmark, we have a free tool where you can actually calculate all these, do these calculations, and there's a library of materials. There's also starting to come proprietary calculation tools. I don't know how used they are yet, but there's an industry for this now. So we do have a very low barrier, and that is one of the reasons that we have progressed so fast here in Denmark, that there is a free tool available. And what we see already is that no matter where you are in the value chain in the construction sector, if you're an architect and doing the very early design phase of a building, you have to incorporate knowledge about what is the result in CO2 emissions. What is the materials, the amount of materials, even though you're only doing volume studies on the building, this is a part you have to take into account if you want to be able to compete in architectural competitions. When you're starting to be more detailed in the design, you have to choose between what kind of materials are you going to choose for this indoor wall or for this roof. You have to be aware what is the resulting CO2 emissions. So and of course, when you go to the contractor who has to buy the specific brick or the specific board or the insulation material, there is a competition between the different producers who has the lowest CO2 emissions. So now it's an economic factor. If you want to be on the market, you have to have data, and you also have to have comparable low CO2 emissions to be at least if you want to have a quality product that you can take money for. When we started 10 years ago, there was maybe a handful of EPDs, environmental product declarations, for specific materials. I don't know the exact number today, but it is in the thousands, and it is a European standard scheme we have. So you can buy for Norway or Denmark, Germany. It doesn't matter. You have the same data and the same data quality, so you can implement into your calculations on the building level. And just to give some kind of visualization, what does this mean? This is a project, some social housing project. It was finished in 2018, so it's 2020, and it has a final result of a little more than 6 kilos CO2 per square meter per year. It's mostly made by wooden construction. I don't remember exactly what kind of insulation material, but I think it's mineral wool. So But there is a lot of biomass actually in this building. And if we look at the different kind of phases in the life cycle of the building, we can see that actually the high CO2 emission from this building is going to be in the end of life phases. That is the C3 and C4. That is the end of life, and that is the burning or the decomposing of the biomass in the building. We can also see that the module D, which is the potential for if we calculate as if we reuse materials or if we actually take into account the offset of burning biomass and not coal, that we would have a quite a high negative CO2 emission in the potential for in the end of the life cycle. So biomass is one of the options you have if you want to lower the overall CO2 emissions of buildings. The other, as a primary building materials, is the concrete, which has a high CO2 emission in the burning of the cement, and steel, which also have a high CO2 emission in its production. In 2025, there's going to be a adaptation of the building code where we lower the limit values for the global warming potential for the buildings is going to be lowered quite a bit. So, for example, for single-family houses, it's going to be 6.7 kilo CO2 per square meter. For office buildings, it's going to be 7.5 compared to today where it's 12. So it's actually a quite big step down. We are also going to take into account the construction process, so the energy use and the transport to the building site. But that doesn't make such a big change for biomass building materials. But just to take it into like an historic context, when we started out 10 years ago, if we looked at the multi-story dwellings in the GGNB system, our point scale for the global warming potential was from almost 15 up to 27, 28 kilo CO2 per square meter per year. Today, the limit value is 12 for all buildings, and it's going to be even lower in next year. So it has fallen quite a bit, our ambition on what is the CO2 emission from buildings in a life cycle perspective. And to give you like just a background for how is that even possible, when we look at like a reference building, where is the CO2 emissions from? I've made this reference for a standard building in the green columns. The dark green is the operational energy. So what we see is that there have been a 95% reduction in CO2 emissions from the operational energy. It's both based on more energy efficient buildings today, but mostly it's about the decarbonization of our energy systems and the projections from the future that is going to be even more renewable energy in our energy systems. So we are going from being the dominant part to being almost negligible in a life cycle perspective of buildings. So today the focus is primarily on the building materials in Denmark. It's not so all over Europe. In Germany, it's completely the opposite, but in Denmark, it's the building materials, and everybody is trying to find how can we design and have a value chain where we can ensure that we can build our buildings also in the future, in 25, in 27, in 2029, where the tightening of the limit values in the building code is going to be much lower than they are today. So we have actually in the building industry made this a marketplace for CO2 savings by having transparency and incentives for all actors in the building industry to how to lower the CO2 emissions. And the building materials is a big part of it. I think that was the quick introduction to what is happening in the building industry.
Thank you very much, Lau. That was a really good insight into the building industry and the changes that are happening. We could have 3 minutes for questions. So if there's someone with a question, please raise your hand. Uffe, you have a question?
Yeah, I totally agree. Nice overview. And I think it puts the biomass challenge in the building industry into a nice perspective, because I think this rule of combusting all biomass after 50 years is really strange. I agree on taking a limit, that could be okay, but I see no way that we in 50 years will combust our biomass resources without utilizing the CO2 again, or even better, of course, to reuse the construction materials in some way. So I think your option of having a D value was nice, but is that taken into account in the official regulation? I'm not. I think they are not.
No, exactly. You are spot on. So what we have done in the DGNB system, we try to be ahead of the curve and look at what is going to be the future. So I have another slide. I'll just show you this one, because we are trying to the way we evaluate the buildings that are going for certification, to say, well, we know the future is going to be different. We already take it into account in our energy system. We should also take it into account for our building materials. So we are implementing a technological factor with a 1% lowering of CO2 emissions per year, to take into account better production facilities and in changing in the energy system, but also changing in the end of life cycle, the waste management. So what it actually, we're also taking into account like a time factor, because the CO2 emissions in the future has a smaller overall global warming potential than if you emit it today. So we want to have more focus on the upfront carbon. And what is the effect of that is basically to say, if you store biomass, biogenic carbon in your building, you get a net negative at about 40% of the carbon as a result. So we want to give a much bigger incentive to use carbon biogenic materials in the building. If we can make that as the default also for the regulation and the EU, is I don't know, but we want to go that way.
Thank you very much. There is also a Boholm Jacobsen wrote a question in the chat. Maybe Lau, you can answer that while we move on in the program, and we can come back to maybe a little bit more discussion later. But so definitely it's clear that there will be a market pull for new sustainable and bio-based materials. So now we'll have a look at what are some of the examples of bio-based materials. And the next presentation will be, we have invited Julian Christ from University of Copenhagen. So if you share your presentation, Julian, and you can start whenever you're ready.
Can you see my presentation and can you hear me?
Yes, that works, and we can hear you and see you now.
Fantastic. Yeah, good morning, everyone. And thank you very much for inviting me to this exciting seminar. I think it's very nice that it covers so many different fields, which kind of have the same or like some of shared perspectives. And I would like to introduce you today what we're doing at the Department of Geoscience and Natural Resource Management in terms of developing bio-based construction materials. First, a little bit about myself, since I think like many of you don't know me, maybe some do. I've been researching in biomaterials since 2017. I focus primarily on researching in biologically based binders for construction application, but also have a background in automation for construction processes and structural engineering. That comes both from DTU, where I did my PhD, and I'm currently employed as a postdoc here at the University of Copenhagen. So to start to introduce these fields, we have huge challenges in the construction industry. Like the UN Habitat expects that 3 billion people, so 40% of the population, needs access to adequate housing until 2030. So that's 6 years. And that means that we need to build 96,000 housing units every day. So that translates to understandable numbers to a floor plan of Paris every week. That is expected to double the material consumption, double the raw material consumption. To the same time in construction, we have the problem that our productivity is declining or is stagnant because of shortage of skilled workforce. So we need to optimize our processes and automate more. And also the building and construction industry, as we also heard from Lau, is a major polluter, and 39% of global process and energy emissions are related to the sector. So what can we do about this? We can, from our material sector, our material research point of view, we can diversify the materials market. So we can supply a lot of more bio-based and renewable materials that can supply more of that what we need, which is building materials, and can potentially also increase the productivity, because we can get away from old not so effective building methods which need a lot of labor. And of course, then you can also recycle and potentially reuse those building materials which we're talking about. So here today, I will tell you two about those ideas or solutions, and one of them is the hashtag project, which I also said I would present here. So that there we're using bio-based binders from grass resources, from lowland fields here in Denmark, for the application in wooden boards. And then Morten said in the program that you wanted to hear some concrete examples, so I couldn't say no to present also some concrete composites which are bio-based. And so then I'm also presenting a project which was my PhD project and is also currently further developed. So let's start with the hashtag project, where we're using grass, which we harvest. So this hashtag project is a relatively large project funded by the GUDP, and there a lot of different components play a role. So like one is the development of machines that you can utilize those lowland soils, and where you can harvest those grass, and then you can extract those proteins, which is also part of the project, for a multi-purpose use, so also for other applications or for food applications. And we are also trying to make adhesives or wooden boards out of it, so for plywood and for particle boards. So the aim of this project is to elevate the sustainability of the construction industry and the furniture industry, and present alternatives to petroleum-based adhesives which are currently widely used. So here you can see some of the first examples which we published last year. So this is our working horse machine on the left lower side, where we can glue 2 pieces of veneer together with our protein adhesive. And then when we drag it apart, we measure what the maximum shear strength was. And then we get an idea if it's a good glue or if it's a bad glue. And in the US, they are actually using a lot of soy protein already in industry scales as well. So they did use that in the natural economy, as Uffe also said, with these 3 steps with the natural economy, fossil-based economy, and bioeconomy. So soy protein was used in the natural economy, then got replaced by the fossil-based economy with fossil-based glues, and now they're coming back to it again with the soy protein flour. And here to the left, you can see this soy protein adhesive, which has a strength of around 8 megapascal, and with the first trials of the grass protein, we actually come to maybe 75% of the strength of what the soy protein has from before. So it is in the order of magnitude, but we are developing further on, and now with some new compositions, we can actually see that we can make some wooden particle boards out of it, which are just using protein-based glue from lowland soils. So this, as I said, this was funded by GDP, some main collaborators, and at the University of Copenhagen, it's me involved and Anand Ramesh. So another point where we're using bio-based binders from local resources is this concrete example. And here we want to replace some of the high energy intensive cement used in conventional concretes, and we want to replace that with some bio-based binders. So here you can see some of the composites. What we used for this, there was byproducts from the meat and fish industry, so mammal gelatin and cold water fish gelatin, but also chitosan, and also algae-based binders, sodium arsenate, agar, and copper carrageen. And we wanted to use this for 3D concrete printing. And here you can see a conventional process from Cobot in 2019. And there they're using conventional cement. And for those special rheological properties, like for those special flow properties, you use a high share of cement. So it saves maybe material, but you need to put in even more binder that's energy intensive. So that's also why we want to introduce a bio-based binder for this. And those bio-based binders, they also have the nice properties so that they melt when you heat them up, and then they cool, and then they stiffen up when you cool them down. So a 3D printing process is actually a lot more effective than with conventional concrete composites. So we did some mixtures of those materials, put them in a compression test, and we can see here that the cold water fish gelatin as a binder performed actually the best. There we go up to 60 megapascal, which is in the same order of magnitude as conventional concrete. And we could prove that we have those really good flow properties for the 3D printing. So we could actually 3D print not only straight up, which you would do with conventional concrete, but we could also print in basically any direction, which gives the chance to minimize and optimize constructions even more than you do with 3D printing of conventional concrete composites. And you can see here that some of these things that we printed with the bio-based binders are now exhibited at the Design Museum. So that project was partly done at the DTU, but we're also working on some of these things currently, and it was funded by Willumfonden and DTU. And then I can conclude with those are two examples that we are working on, which could potentially diversify the materials market and bring us more or maybe more effective use of biomaterials, of construction materials, sorry. And then I would also like to advertise our section, which does a lot of work in bio-based composites generally, wooden materials, and bio-based adhesives. So thank you very much, and hope we have time for some questions.
Yes, thank you, Julian, for the nice presentation. And indeed, we have actually time for questions, and now we managed to get some time back. So I can see a hand from Knud Tybjerg from Food and Biocluster.
Hi, thank you, Julian, for your presentation. I think it was a good overview. I have a general, say, concern or a dilemma about composite materials. So we mix bio-based carbon with fossil resources that are, well, mineral fossil materials, like, well, in construction, as we talk about today, but it's the same thing with wind turbine blades and things like that. How do we come across that dilemma? Because I think that in construction we need some mixtures of different substances, but for me it's a dilemma how to separate it in the end, as we talked about earlier on the phase of where to break down the buildings or to burn it or what to do with it in the end. Just do you have any comments on that?
Yeah, thank you very much for that question. I think it's a really good one, and I think it also underlines like why we are researching in the field of bio-based binders. But let me start from where I see the future of constructions. I see the future of construction for sure bio-based, and I think like we're going to build a lot more out of wood and out of timber. And I think like a lot of this timber can be reused. Like you could just shorten it and then put it as a new beam in a new building, which has maybe a lower span or something like that. And but at some point you can't have that small buildings anymore, because then you just cut it down more and more, and it will at some point be a particle. So, and then we need to we still don't want to burn it, but we want to sequestrate the carbon even longer in our buildings. And I think then composite materials come into play. And I've done some experiments also with wood plastic composites, for example, where you have like a quite high share of fibers, of wooden fibers, and then you bind those fibers with some petroleum-based plastic. And I think like this works really good, but I think we should find bio-based binders so that we can first of all easier recycle those materials, or then in the end also let them degrade and not be a hazard for the environment. So that question pretty much sums up why we are researching in bio-based binders. Thank you.
Thank you. Uffe, you have a question?
Yeah, sorry for interfering again, but very interesting overview of potentials. But don't you think about also trying to make a fully grass-based board? Because if you can make the binder from the grass, you could also use the grass fibers instead of wood fibers, couldn't you?
That's correct, and we're working on that, yes.
Yeah, that's good.
Yeah.
If I may add to that, I think that one of the challenges is that you have to remove the wax around the grass straw. So that's one of the challenges to make a particle board of grass particles. And I think that we have enough leftover wood to make the particle boards being used in Denmark as it is now. So we don't need the grass at Kronospan. They don't need the grass. They have enough wooden-based chips to use for it. But I think there's work being done on removing the wax and see if that has a higher value also in the Høstek project.
Yeah, but I also think, like, I mean, we do have the problem that like all those binders, they have a durability problem, and I think like then we do also need to investigate whether or not different substrate have a influence on these properties and which are maybe beneficial.
And maybe that this is also a comment and maybe also a question that even though that the current production of boards in Denmark in a specific company could have enough resources, it looked clear to me, Julian, in your introduction, that we need more materials in general, and maybe also new materials that can do something slightly different than what is like state of the art today. Is that okay to look at it like that? I'm not from the materials industry, so.
Yes, I mean, I think it's key to find some building materials which also give room for new processes, which are maybe not so labor intensive. So, like for example, with this 3D printing, what we did here, that we lever on the material where we gain a property from the material, where we can then design a process which is less labor intensive. Of course, it will not end up that like this material which we develop will replace concrete, because concrete is just I think the second most used material of humankind after water. So it's a huge mass we're using, and we will not replace this with one solution, but we can rather find different solutions, maybe for different regions or for different industries.
Okay. Thank you. If there are further questions, please add them in the chat, and Julian, you can have a look there, and maybe also if there are questions to other previous presenters.
Thank you.
So I will go on, not presenting myself, but I will just share a presentation. Okay. Oh, stop. Okay, do you see my slide now? Yes. Okay, thanks. So I will end this short, intense webinar with the last presentation, talking about how we see this the role of perennial crops such as grass, could be other specific crops, but perennial crops through green biorefinery, and how that can also supply substrates for biomaterials, coupling food and materials production. So in my presentation, I will first of all look at this more of a system perspectives, and then in the end I have 3 examples of biomaterials we have and are still working on. However, they are not exactly building materials, but there are similarities. So just as short, the green biorefinery of perennial green crops, we have been working a lot on that in Denmark in general, and in Aarhus University we have developed also upscaling the technology with a focus on simplicity, practicality, and bulk applications, primarily to produce a protein concentrate that can substitute soy import for animal feed, and later for food, and also substitute the soy import for food and animal protein. The fiber can be used for ruminant animal feed, or otherwise go to a biogas plant, generating energy and securing nutrient recycling. But as Uffe explained, the main motivation of this is actually to develop a profitable and robust value chain around a rural green biorefinery, because that would enable new possibilities for farmer to change from the annual cropping systems to perennial cropping systems, and thereby get the environmental benefits of reduced nitrogen leaching, pesticide use, soil carbon, and also biodiversity potentially. There are also some arguments on the technology development and increased business possibilities in rural areas, and on the product side, especially about the feed and food production, local production, and more sustainable alternative. And then if we look at if we have a look at the fiber fraction that is in the basic scenario going to ruminant feed or bioenergy through biogas, there is also a potential to use that for building materials, and that would also have an argument of potential increasing the potential carbon sequestration from this increase in solar radiation and photosynthesis on our agricultural area. So we take up CO2, we store it both in the plant above ground and below ground. Below ground, this will vary a lot, but have to 1 ton carbon per hectare per year, depending on the area. The above ground biomass will be in the range of 4 to 6 tons carbon per hectare per year. And if we just say that maybe 1/3 or half of that carbon could be used in materials, that would also have a storage potential. I will not go too much into this because Uffe already presented it, but from these scenarios that Uffe presented in the morning, we have taken this potential of new perennial grasses or perennial green biomasses and put it into a larger system of all the bioresources we could have available in 2030, and what kind of products we can get out of those. So quantitative inventory, translating those bioresources into proteins and carbohydrates and lignin and ash, etc. I'll not go into detail here, but by applying a cascade exploitation principle, you can use the proteins in food and feed, lipids also in food and feed, carbohydrates in biochemicals and biomaterials, but also biofuels, etc., etc. With this approach, we have modeled the total input of biomass, and here we see this also includes all the green crops, the grassland crops, but also the industrial side streams and yellow straw. The energy wood is also in on this as an input, but through green biorefineries and other future biorefineries that extract and separate these bioresources, this is just the potential that could be. And also we will end up with a significant amount of lignocellulosic biomass, not including, of course, the wood that is good for building material directly, but lignocellulosic biomass, where we have potentials We have the cellulose and hemicellulose, the carbohydrates, structural carbohydrates there, the lignin, and residues for other stuff. So if we look at how much bioresource potential we have, there is some part that would be quite good to use in the feed and the food system, including the proteins, the simple sugars, and the lipids, both ingredients and bulk feed here. Then we have this fraction of the lignocellulosic biomass for materials, chemicals, perhaps fuels also. And then there is, in the end, in a cascade exploitation, a potential for fuels, carbon storage, and fertilizer, depending on what we choose, what we prioritize in the future society. So that's just to say how important these biorefineries will be in the future for channeling out our resources for all the products that we need, both materials but also chemicals, fuels, energy, carbon storage. And if you look at the amounts, these, for example, just the amount of cellulose that is potential out here is 3.25 million ton dry matter. And if we look at the business as usual scenario up in the up left corner, the total bioresource in that scenario is only 2 times that. So there is a big potential for bioresources through and channeling through green biorefineries if we convert the agricultural system. So now I'm going to go into this green biorefinery. So in the basic scenario, as I talked about, the fiber goes for feed for ruminants or as a substrate to biomethane and biogas. However, the business case of this basic scenario is not it's not exactly great. It is challenged, and we need either to add more value in the product outputs, or of course general optimization, or support these new sustainable systems with some kind of support scheme. But on the side of increasing the value of the side streams, well, actually the fiber from such a green biorefinery would resemble 60% of the total dry matter input. So what can we do with that? Well, we have been working with thermal conversion, pyrolysis, hydrothermal liquefaction. So that's a possibility for energy, biochar, carbon storage, fuel products. Another option is a lignocellulosic biorefinery where we fractionate the lignocellulose. We still have some protein. We also can fractionate. There is, as Knud mentioned, there is the waxy layer, which is lipids, could be extracted and used for something higher value. And then we have applications in biomaterials. And so here I put some examples, insulation materials. This is already commercial. There's a company, Gramitherm, producing grass fiber in insulation mats already. Biocomposites, this is also done. There's a company, Biovert, which takes the fiber material and make composites with plastics. Horticulture substrates is another alternative we have been working on. But then what I will talk about now is the option for also paper and packaging. So using the cellulose, similar to wood cellulose, but presenting an alternative for that, so we can use our wood for better applications or potentially also not cut it down in areas where that is prioritized. And then I will talk about also cellulose-based textiles. So as an example for biomaterials of the grass fiber, we have been part of a big European project, GoGrass, where the partner in the Netherlands were working to make, actually this was on roadside grasses primarily, and grasses that were not used for protein production, but they made a process for making cellulose-based paper out of for grass. A lot of development in the lab, and it actually shows good properties. They scale it up. It is a process that combines a dry digestion, similar to anaerobic digestion, a washing, a alkali treatment, and a milling. And then they get a cellulose pulp, and they just, when the project ended here in the spring, they managed to make a full-scale first industrial paper making at a, well, for the industry, quite tiny paper production facility, but still a commercial paper production facility. So that's a good example of the cellulose could be used for. In GoGrass, we also collaborated using some of the grass that we have from our protein extraction green biorefinery system, and this also showed potential and will actually be continued developed in a new CBIO European project. Yes. A similar example is that we have had taking part in a GODP project, Simpropac, where we use the grass fiber based paper for sustainable to-go packaging products. So cups and plates, things like that, to substitute plastics or bioplastics or wooden cellulose packaging. And the project was coordinated, and a lot of the processing was done by the Danish Technological Institute, and we supplied the biomass from some of these paludiculture sites that Agroecology are working on, and Claudia talked about. So the grasses from there, we extracted protein, and the press cake went to Technologisk Institute to look at the properties for cellulose-based packaging. And one of the things that was found is actually that we could. It showed really good strength. So it had really high internal fiber bonding and wear resistance. So could also be relevant in areas not maybe to-go packaging, but where you need a really tough packaging product, wrapping a computer, for example, something like that. And then the last example I have is something we have been working on for quite some years, but not very intensively. We haven't had too many projects on it. Now we are working on it in a Interreg project called Green Valleys. So utilizing the grass fiber for textile production. So in the global fiber production for textiles, well, it's primarily plastics, so polyester, but of course it's also a lot of cotton, and then what is beginning to rise is the use of these man-made cellulosic fibers. It's a well-known concept. Viscose is an old example of this. but there are increasing amounts of new type of man-made cellulosic fibers, but all of them primarily focusing on the wood cellulose. So we are working on using the perennial grasses and using the cellulose in these grasses. We'll have the wet fractionation extracting proteins from it, but then pre-treatment and refining of the press cake fiber, solubilizing the cellulose and spin it as a fiber in a fiber spinner, which is there's a picture in the bottom of this page. We are at the stage now that we can create these fibers from different materials with different types of treatments before that, and that fiber will then need to go in to make a thread and make a yarn and make a fabric. So that is still to be done, but working progress. Okay, and I think that is what I had for my presentation. So if any of you have questions specifically to my presentation, we can have that, and then we broaden it out to a more broad discussion maybe. Okay, if there's no questions specifically to this, I think I can maybe spark a discussion that in my view it's clear that there is a market pull for new materials with a better sustainability and carbon footprint, and also the combination of trying to reduce environmental impacts in the primary production. I think materials can play a really important role in the future, because some of these new crops we would like to start having much more of have considerable amounts of biomass which is not fit for food, and would need to be used in a different sector. So the coupling of this reduction or change in the agricultural system with new market pull in new sustainable materials is, as I see it, a really big potential. So if any of you have gotten good ideas while listening to these presentations in the webinar, please you're welcome to share them, or send us an email if you want a contact to any of the presenters. We will happily provide that. I can see that Lau Reffensø from the Green Building Council left the meeting. He had another meeting he needed to attend, but we can also provide the contact there. But are there any of you that have any comments, ideas for this topic? Julian?
Yeah, thank you for this great webinar. That was really interesting, generally, to everyone. And I would just like to raise a question. Like with those numbers I presented, that we need to that we double our raw material consumption just within the construction industry, for example. I mean, like all those bioresources which we are dealing with now, and also with wood and so on. There's a lot to get, and I agree with us on that, with us all. And but I think at some point also those waste materials, or if it is waste materials, byproducts or side streams, also those will be used and utilized and like all those biomaterials are linked to a limited resource, which is land use. So if we're seeing the bioeconomy in the future, like which bioresource would be the best to utilize to get away from that land use?
Thank you. I think this is a really important point. There will be a fight about resources between many sectors in the future. I'm absolutely sure. I have been fairly involved lately in also the developments of the Power to X sector, which needs immense amount of carbon for the green fuels we need to substitute the fossil fuels. The amounts are just huge. So actually it would be this about providing an overview of what could be possible and what is actually needed. This very complicated figure that Uffe showed in the morning, we didn't go exactly through it, but actually there the take-home message was that even though we apply these high biomass resource scenarios, we will still need direct air capture. So maybe a reduction in the need is definitely, well, maybe definitely a reduction is definitely also needed in my view. But Uffe, you have a comment on that?
Yeah, it's of course a relevant question, and I think there will be a fight. But to put it into perspective, we have in a project we are running with funded by Realdania and with Artelia. Artelia made some scenarios for the need of bio-based materials in future building, and that of course can depend a lot on how much we build. But some kind of just building like we do today, we would need something like 0.6 million tons of biomass each year for the Danish building sector. And the scenarios I showed potentially can provide at least 10 million tons more than we use today. So it's actually just a minor share that is going for the building sector. But then including all the other sectors, of course, there will be a fight about the resources. But I think there's no reason not to get started. And from this seminar, I am actually thinking that we need to go to the demonstration phase. We need to showcase some of this potential. And I really liked some of the material that Julian showed, that we can make something. And we also saw the small, tiny houses from Germany. And I think this is a way to show around us that this is possible. And of course, we need to discuss how to do it. But showcasing is a good thing.
Are there others that have comments to this discussion or want to spark another one?
Hi, Morten.
Hi, Kirill.
Maybe I have a comment inspired by some of the lectures with my colleagues, with our colleagues, Johan and Matthias here in China, that maybe we should be more modest when it comes to carbon sequestration in the soil from perennial grasses. It seems that in our expectations, it seems that the effects are more robust on a shorter time scales, whereas on the long time scales, when it comes to primary production, as any cropping systems, grasses are not different, and it is rather postponing an emission, not sequestering, because once these systems are terminated, they will emit CO2 and N2O in magnitude, which is very dependent on their quality. So how much also mineralizable nitrogen and decomposable carbon they have. This is on a longer term. On a short term, I think, we have much better news to share when it comes to the primary production. So I'm in the field cultivation. Uffe?
Yeah, now this is a nice discussion, Kirill. I tend to disagree a bit. I'm sure there will be some changes over time. Also, because we have increasing temperatures, we will have a risk of decreasing soil carbon contents, but that will still be a difference between the perennial systems and the annual systems in the level that they have. If we make a change into higher share of perennials in our agricultural system, of course we need to keep that change. It's not something we do for 10 years, it's something we will do forever. Otherwise it's lost again. I agree.
And I think also it's a point about, well, we need to discuss what we prioritize our resources for. And of course, biochar and carbon sequestration through pyrolysis is an option. But there's also if the carbon is almost as good stored in a building, because we are not tearing it down anytime soon, and when we will recycle it and so on. It would maybe be a better solution, but we need to show that, and we need to show that the carbon is fixed also in the building materials, I guess. Kathy, you have a hand.
Yeah, I just wanted to say, I think it was some really interesting presentations today, and I'm sitting in Skive municipality, so working at a local municipality where we're sitting with this. And I came to think when Uffe, you showed those maps about, you know, how much space is left for agriculture when you take into account all the other things. In that map, I don't remember, but I mean, in our municipality, we're also struggling with where do you put renewable energy? Because, and are you looking at that? And I know there's been some work about, well, can you have solar panels that are vertical, and is energy production part of that map that you had with, you know, taking out for areas that need to reduce nitrate leaching and all that? Because then there's even less space, I think.
No, you're totally right. That's another point, and we didn't include that. There's no planning in this area. There's no one finding out where the right places are for the installations of maybe of wind power, but certainly not for solar. And there's a great need for planning in this area. And we are trying to develop systems where we can integrate agriculture and PV production. It's called agrivoltaic. I think we can do it, but we cannot change the visual impact. That is still up for discussion. But of course, taking land out of intensive production on the nitrate sensitive areas and raising PV panels and then have some extensive grazing of sheep is an option.
Yeah, and I'm also wondering, and this is a little bit far out, but depending on how much water in this polyculture, and this is maybe more for Claudia, but depending on how much water we're talking about with re-wetting of peatlands, could you also have energy installations there? I mean, I don't know if you can have water panels, if solar panels, if the water level isn't too high, and then I don't like. It's about getting as many win-wins in the same area as possible, yeah. I guess. Yeah.
The companies are planning to do that. Yes, to combine the re-wetting and raising of solar panels. I think the piloting is could be quite difficult, but they are working on that. I think the big question is then, do we like to have solar panels in our nature areas? I think that can be a long discussion.
Agreed.
Thank you, Kathy. Are there other comments or questions? I think there is a lot of things going on the material side in Denmark, but also outside. And I would just take the opportunity to say that in CBIO we are very interested in collaborating in this area, expanding the possibilities, looking for new research areas or where research can help the development and implementation of new biomaterials. So that is a message. Dana, you have a hand?
Yes. Hi. I'm just wondering about the biodiversity in all of this. Have you a focus on going from monoculture to permaculture and agroforestry and stuff like that?
Maybe you can answer.
Should I give a comment on that? Yes, it's the way we have quantified impact on biodiversity in our scenarios is the land area that we take out of intensive production, and it was up to, in some scenarios, 500,000 hectares of land, which is quite a lot, more than 20% of the total agricultural area. Then, of course, you can also try to increase biodiversity on the agricultural area. That's one of the purposes of organic production. You can also apply agroforestry. Yes. What we are working at is also the grasslands to make them much more diverse. Instead of pure grasses, it can be grass clover. But we are also having trials with up to 16 different species that complement each other, and then we can have much more flowering for insects. And it's quite interesting. We can actually also apparently keep the productivity. So I think there's a lot of interesting work to develop if we have a new sector here, also to make it a biodiverse sector.
And if I just can add to that on the processing side, it's not per se a huge problem that it's a diverse raw material coming in. It will of course impact the product, but not necessarily in a bad way. So I see a big future for looking much more into utilizing mixed cultures for different purposes, also through biorefinery, but not as the sole use, of course. Good point. We definitely need more biodiversity. Bo Holm Jacobsen, you have a hand and a comment, maybe?
Just a brief one.
Yeah.
Can people eat grass? I mean, the protein that comes out, can it also go to products that people can eat directly?
Yes, thank you very much for that question. So we have in the development focused on the feed, because that is the bulk product where we have the huge amounts and the big issue with soy import. And also because technically it's much easier to produce a feed quality than a food quality. There is nothing sort of to hinder that humans eat the grass protein. However, the feed protein concentrate contains still all flavors of grass and can contain amounts of anti-nutritional factors, so in larger amounts. And this is but we are working on in several projects on advancing the technology, getting what we call a more white protein isolate out, which definitely has potential in food industry. There could also be other ways of using fermentation or something else on the products, but we haven't looked too much into that. And then there is the biggest obstacle for using the grass protein in food. That is the EU novel food regulation. So all new food needs to be approved through the novel food regulation, which is a good thing that we can secure safety food products. safe food products. However, the process is lengthy, complicated, and when you apply for one application, it's only for one specific product. So we still haven't fully got an answer whether if we get an approval of a grass protein isolate as a food, if we then change the biomass slightly to another type of grass or clover, if we change the process to a slightly different, if we then need a new novel food regulation. So there's a big regulation issue here, other than technical stuff. But we're working on that, and we are as we speak producing white protein isolates at our demonstration facility for tests. Okay, with that said, we also went 2 minutes over time, but guess that's okay. Thank you very much, all of you, for sticking around and joining the webinar, and see you for the next webinar, maybe.